All right, real quick video here. We want to look at waters of hydration, which is a goofy bit that goes back to really thinking about what an ionic compound is. When you first studied ionic compounds in grade 9 science, what you probably talked about is that ionic compounds are a series of ions that are held together because positives attract negatives and negatives attract positives. So at the very simplest level, we could have something like sodium chloride, right, where we'd have a sodium ion, and that's going to be next to a chloride ion, right? Sodium ion is a plus charge, chloride is a minus charge. And then if we were to kind of look at this in, well, first of all, 2 dimensions, this chloride is going to be next to another sodium. And in fact, in 2 dimensions, it's surrounded on all 4 sides by a sodium. And then each sodium is surrounded on all 4 sides by a chloride. And what you get here is what's called a lattice. All right. And the neat thing here is we can imagine this extending in 3 dimensions towards us. So that means on top of this chloride here, towards us out of the screen, is going to be a sodium. So it's going to come out this way, and now we have a sodium ion. And then on top of this sodium here, coming out of the screen, is a chloride. And on top of this chloride and so, right, is a sodium, and so on. And this just continues out in 3 dimensions until the edge of the actual physical crystal. Now, sodium chloride, both sodiums and chlorides are pretty small. And there's 1 sodium for each chloride, and so the shape of it, now, by the way, the shape stuff is well beyond science 10. But take my word for it, there's not much room in between the individual ions. And so this waters of hydration bit doesn't really happen for sodium chloride. But if we were to look at something different, for example, this copper 2 chloride, we take a solution of that and we allow the water to evaporate. Water evaporates and leaves the ionic compound behind, right? This should make sense. You've talked about this in grade 8 science when you talked about separation of solutions, right? You can use evaporation. So if I have salt water and I want to get the salt back, I let the water evaporate and I'm left with salt crystals. But depending on what the compound was, some of the water molecules are going to be trapped inside the solid crystal. Other times, humidity in the air can itself become trapped inside of a solid crystal. These water molecules become part of the mass of the compound, and they must be accounted for when we write the formula. Now, happy thing here, this part here. You will always be told how many water molecules there are because you cannot predict these things easily, okay? We name these by naming the compound, and it's whatever the ionic compound is. So all those other names that we've talked about. And then this is the new part, some kind of prefix, and then the word hydrate. So copper 2 chloride, and then there's 2 H2Os after it. That's how you write the formula. We would name this as cobalt, Roman numeral 2 chloride. Cobalt, remember, doesn't have to be a 2+, and so this tells us this is the 2+ version of cobalt. And then there's 2 water molecules associated with every cobalt 2 chloride. And so we call this thing dihydrate because di is the prefix for 2. Okay. If I have NaOH, sodium, then I find OH. Oh, that one's not on my periodic table. And then I go, oh yeah, wait a minute. That is one of my polyatomic ions. So that's going to be sodium, and I find OH is hydroxide, and then there's .7 waters. I'm going to name this as sodium hydroxide, and then I find the prefix for 7, which is hepta. So this is sodium hydroxide heptahydrate. All right. So I'll show you here. You have these in your notes. Anyways, in terms of the prefixes, you'll never really have to go past 10 if you care. We can have 11 and 12. There's many. You could go up to 20, I believe, is icosa. There is one for all of the numbers. That being said, usually 1 to 6 are pretty common. 7 actually shows up more than you'd think it should. Deca shows up once in a while. Octa and nona, not so much. So a couple examples. Need to look at those. So first of all, let's take a look at a couple examples here. What if I give you MgSO4 dot 7H2O. First thing I have to do is name the ionic compound. That's no different than what we've been doing. This turns out to be a polyatomic thing. Magnesium can only ever be 2+. So if I'm showing all my work, Mg2+, SO4. Oh yeah, this is one of my polyatomic ions. So this becomes SO4 2-. I have 7, so I come over here and find, oh yeah, there it is, hepta. So it's going to be something heptahydrate. So Mg is magnesium. SO4, I know that is the magnesium symbol. I need the actual word. Let's try again. There we go. So I have magnesium. That SO4 2- thing is sulfate. And 7H2Os means, okay, and I'm going to write this on a separate, actually I'll go even up beside it. Make it so we can all see it in one straight line. Heptahydrate. All right. One last example here. What if I give you the name? Well, I'm going to give you the name of sodium thiosulfate. Pentahydrate. So, it takes me forever to write this out, but we'll deal with it. All right, sodium. I write down the sodium ion. That's Na+. Beautiful. I find thiosulfate. S2O. This isn't. Oh, settle down there. S2O3 2-. Look at this and I go, okay, I gotta come up with a formula for this. And again, the hard part maybe for thiosulfate is not writing this part down, it's maybe finding it. So it is one of your polyatomic ions. So we've got Na+. Oh, I need 2 of these. Because I've got 2 negatives, I need 2 pluses. Okay, so I got 2 of those. So my formula is going to look like Na2 S2O3. And then I think I'm done, but I'm like, oh no, pentahydrate. Dot 5H2O. And really, that's the bulk of it. Lots to work on in your booklets. Have fun.